Wonderful. Thank you, Pam. Okay. So, yes, thank you for the invitation. I'm excited to talk to you all about one of my favorite topics, mostly GPU programming with Julia. My name is Valentin Sharavi. I'm a postdoc at the High Performance Scientific Computing Laboratory at the University of Augsburg and also a postdoc in numerical mathematics at the University of Mainz. There we go. My goal really in life is to make accelerated computing and high-performance computing more accessible, both to scientists and engineers, but also for people learning HPC and people who want to take their programs, essentially, we often say, from a laptop to an HPC center. I work mostly with science teams to help them get the most out of Julia. So I've been a part of the climate science project Climber that started many years ago now, and then various other projects over the years. As a brief background, I did my Bachelor's of Science in Cognition back then, thinking about how robots might be able to think in cognitive science in Osnabrück. I spent some time in Japan, and then I did my PhD in computer science at the Julia Lab. And since last August, I'm now back in Germany, working in Augsburg and in Mainz. So what is Julia? Well, Julia is, for me, my favorite front-end to LLVM, but for most other people, it's a modern, dynamic, general-purpose compiled programming language, which has the great benefits of being interactive. So you can use it as a modern calculator, but you can also use it in notebooks, like I'm doing right now. This is a Pluto notebook, so that's a observable notebook where it solves a couple of the complaints we have about Jupyter, where Jupyter is very stateful. And of course, Julia has all of the feature comforts that a modern programming language has these days, which is a garbage collector. It uses a just-in-time compiler to optimize programs and to get the most speed out of it. I should say, if you're familiar with Java, Java is a tracing just-in-time compiler. Julia is an just-ahead in-time compiler. So those are very different things. So in Julia, you can do a lot of performance engineering that turns out to be really difficult in Java, because in Java, the just-in-time compiler is fighting against you. It stems from a perceived need that we, the inventors had, and we still have, I feel, that there is a gap in programming language design, that there are a lot of programming languages that are great for general purpose, and there are a lot that are very specific purpose, but especially for technical computing, the kind of computing we all do day to day. Really, we had Fortran, and then a long time nothing, and then we had maybe MATLAB, and then people were like, what Mathematica? And in some sense, Julia is trying to be a very flexible, very open, very mathematics-forward programming language, but that is maybe less restrictive than something like Mathematica. The main programming paradigm is multiple dispatch, which is, to put on my programming language theorist hat, a superset of object-oriented programming, but it is most decidedly not object-oriented programming as you might know it from C++. So multiple dispatch, in short, means when we look at a function, we look at the signature of the function, and then we choose which function we will run based on all of the arguments and not on one that is specially treated. One of my favorite comments from the recent years was by Jeff Hammond, who works, I think, at NVIDIA in Finland, where he declared with great conviction that Julia is very, of course, great, because it's basically Fortran for people who are too lazy to get types and has an interpreter. And this is not necessarily untrue. Julia has a couple of characteristics inherited from Fortran, but of course it is in itself more a language that is much closer to a Lisp than it is to a Fortran. So why Julia? This is it's like fun graphics that Mattis Cox came up with. There seems, or at least a perceived difference where we have scientists who are working with high-level languages, Python, R, MATLAB, and the like, and they are focused really on solving a problem. And then we have people who are maybe more on the developer side of the spectrum, who are worried about performance, who are worried about getting the most out of hardware, who want to have guarantees. And they use a lot of C++, Java, Rust, more static languages. And somehow Julia is sitting more in the middle. And it is a very nuanced discussion, because Julia does not give you many static guarantees, but it is performance-wise much closer to a statically compiled language due to type inference and the just-in-time compiler. For me, why I, as a scientist back then and now as a computer scientist, work on Julia, I find it explorable and understandable. Back when I picked it up first in 2015-ish, 14-ish, I had a long stint of writing Java programs, and I suddenly had fun again writing code in Julia. It is very composable, and this is both a blessing and a curse. Composability makes a lot of interesting and surprising interactions between packages, but it also makes it sometimes challenging because there is no one master document that tells you, well, these two packages will interact in this way. Most of the time you're like, well, I wonder if I can combine uncertainty quantification with units to trace my program and to understand what my program is doing, and oh, it works. But nobody told you that it might have worked. You just had to try. One thing is that user-defined types are as fast and compact as built-ins, with very few exceptions. Julia doesn't have many built-in types. Like one of the exceptions here is the memory type or the symbols. Those are built into the language. Everything else you can basically build yourself, and there is no magic code in the runtime that is faster than the code that you have written. And code that is close to mathematics, for some people this is a gimmick, for other people this is crucial. You can actually just write Unicode, and you can try and make your code look like the paper that you based it off. And this can be very nice for teaching, especially if you want to reduce the cognitive overhead for students to understand how the code is implementing the algorithm or the mathematical functions in the paper itself. Crucially, there should be no need to switch languages for performance, so you should never have this urge of writing your code in Python, and then after a couple of months programming, being like, well, now I need to have it go fast, let me rewrite it in C. The goal that we have as language developers is to give you the tools to understand the performance of your program and do performance engineering, and to improve the performance of your Julia code up until it is as fast as a C code that you could have written. Of course, we are very pragmatic in some ways. So we are standing on the shoulders of giants. You can just call into C like shared libraries. It has a very simple function interface. You can call into Python. You can call from Python into Julia. We're trying to be very much not wasteful in where we are investing our resources and where other people, how other people can make use of Julia. This is more or less like, yes, you can write a really fast class library in Julia, but you shouldn't need to unless you have some really interesting requirements. You can just use OpenClass or MKL to get the best performance on the platform that you're computing. So sometimes when you hear people talk about Julia, they talk about this mysterious two-language problem. And it is what I just mentioned, is that sometimes you start out prototyping in a high-level dynamic language, but then the goal or the of having performance forces me to switch languages to a different one. And often these the switch is from a high-level dynamic programming language to a low-level static programming language. What I found and what I've seen in the wild is that often this creates a social barrier between users and developers. We might be writing a Python front end to a simulation code, and we have domain scientists working with that front end, but we are not educating them in how to actually contribute to the C or C++ code that our simulation code is written in. And I have experienced this myself, but in Julia, because the code is in one language, the domain scientists might need to still learn how to write efficient and high performance code. That is, we're not magic. Julia is not magic. That is still something you need to do and you need to think about. But they can start to learn and can look at the code together with the performance engineers, with the HPC engineers, to try to figure out what's happening. And similarly, as somebody who is working with domain scientists, I find it very enlightening to be able to also look at their code and be like understanding it and have a deep understanding of how that code works and not have these barriers of abstraction that make everything harder for me. This also leads to a sandwich problem, like from a pure performance perspective. There is, as an example, you might know the LAMMPS library for molecular dynamics. They have the ability to call back into Python to implement a potential for molecular dynamics simulations. But they have to call into Python to calculate the forces. And because Python is quite slow, nobody's using that interface because yes, you can for like small problems, but for anything big, it is not worthwhile. And so the layering of system and user code is expensive in its nature. It prohibits a whole set of full stack optimization from a compiler perspective. It's much better if we know all of the code and can optimize across function calls rather than just having an opaque function pointer and saying, well, I don't know what's happening here anymore. So I have found, and many of you have probably also found, that HPC not only suffers from a two-language problem, where we have C and Python, it actually suffers from a many-language problem. We have many different dialects, many different vendor-specific dialects. I have to learn CUDA, I have to learn one API, I have to learn HIP, maybe, or HSA, if I really want to get the best performance out of my AMD GPUs. And that leads to this more and more communication and collaboration bottleneck. This leads to this challenge of, well, do I have to rewrite my entire application just to target a new GPU vendor? How do I even get started? How much of my code can I reuse? There's an article from a while back in Nature, which has this funny headline, come for the syntax, stay for the speed, which I feel always the opposite, because people come for the speed and then realize that the utility and the programming style and the community of Julia is actually the biggest draw. Okay. Yes, Julia for research software engineers is a topic I care about deeply. Like research software engineering as a nascent field, we really have to deal with this collaboration barrier in many different ways, right? We have research software engineers who are coming from the domain sciences and who are very capable, and then also have to deal with very low-level questions. And we have the same thing too for people who come from the more computer science side and then have to learn more about the domain science. And so it is an environment where collaboration is key. And I want a programming language that enables that instead of a programming environment that increases the barriers. We have recently released version 1.11. hopefully this, I'm not promising anything, but July, August, we're going to have 1.12. And from a language perspective, we are very stable. Right now, we're focusing much more on latency and infrastructure issues, and the language itself is not changing as much as it used to be. As a language designer, I find that I'm sad about that because I like change and I like playing around with different language idioms, but as a user of the language, I appreciate that I don't have to change my code every other day. We have now much more focused on a wide package ecosystem. Julia has an inbuilt package manager, not like some other programming languages who have, by this count, 14 different package managers and different styles of package management. And we have a yearly developer conference where we put an emphasis on making all talks and materials available on YouTube. And we are now also having, for the second year, local conferences. So there's going to be the yearly development conference is going to be in July in Pittsburgh in the US. And then there's going to be a local conference in Paris in the fall. I think in late September, early October. And I think for all of you who came to this talk, most importantly, we have excellent native GPU computing support. And Guillaume is in the chat. Guillaume is one of the organizers for JuliaCon local in Paris, and he can probably tell us more about when and where it is. It has excellent native GPU computing support. Most notably, and for the most longest standing one is NVIDIA. This has been an ongoing effort in collaboration. After that, we added AMD support. A couple of years before, it was clear that AMD would be the next big thing in HPC. We have support for Intel GPUs we have support nowadays for Apple GPUs. So if you have an Apple laptop with an M series chip and a recent enough operating system, you might be able to do GPU computing in Julia directly on your laptop. And there is interesting developments where we are mostly working on figuring out what is possible, what can we do. And so there is experimental support for accelerators like the Graph Core IPU and a couple of other ones that are more niche and have a fewer users. But it shows that you can indeed take this Julia GPU ecosystem and port it to many different vendors. Julia for GPU programming is interesting in some sense from a design perspective because when we started out, we wrote our changes, the GPU support into the language runtime. And we got the feedback from the language developers at the time who were like, well, you know, we're not that so sure about this whole GPU nonsense. Maybe it's better if you put it into a package. And we were like, how do we put a compiler into a package? And so over the years, we built enough interfaces and infrastructure into the Julia compiler so that we can have a stable add-on package called gpcompiler.gl that will use LLVM to target vendor GPUs. And so you will install it just like you do any other Julia package. And then you might also need a vendor-specific package like CUDA.gl, AMD GPU.gl, OneAPI.gl, and Meta.gl to enable this compiler infrastructure to translate the Julia code to LLVM-IR, translates it then to some format the vendor expects. For CUDA, this is NVPDX. For AMD GPU, this is actually object files. For Metal, it's AIR, and for OneAPI, it's probably SPIR-V, and uploads that to a GPU and then uses the vendor infrastructure stack to launch kernel, to allocate memory, to do computations. but the entire code generation side is a part of the Julia GPU ecosystem and is basically an add-on to Julia as a package. And so the Julia compiler is only used to translate from the written text to an abstract syntax tree, and then translates that to an LLVM IR that is mostly agnostic. And then we feed that back. We do some translations to make sure that this code can run on a GPU. And when we can't make that transformation, we yell at you and say, hey, by the way, we couldn't compile your code because you have a dynamic dispatch here. And then we use LLVM to optimize it further and upload it to your GPU. One of my collaborators, Kaiti Hyatt, years ago, had this wonderful experience where she took her CPU-based C++ code and rewrote it in Julia and also ported it to GPUs and had a very positive experience. And so I like to put this tweet onto my slides. I've talked about this infrastructure a little bit. So at the bottom, there is GPU compiler.gl. It's a package that just deals with all of the dirty business of taking Julia code and munging it and translating it to the right GPU infrastructure. It basically starts at a function call. It traverses the graph of functions that you're calling and collects all of the necessary IR and then compiles that into one binary. Then we have GPU arrays.gl, which is high-level array-based functionality. So if you just want to do a sum or a MapReduce call, that's implemented there generically, and then packages when the packages can specialize it. We have kernel abstraction.gl, which is a vendor-agnostic programming language. I would like it. It's mostly like OpenCL in Notion, but it's a macro-based, very thin translation layer on top of all of the vendor capabilities that we have. And then there's a very tiny package, but it's important to mention if you start writing GPU codes in Julia, adapt.gl can be used to move data and to translate complicated structures from the host to the device. And then, as I mentioned, we have all of these vendor-specific packages. Some of them have been developed with support from vendors. CUDA and NVIDIA has mostly given us support in terms of hardware donations. For AMD GPU, we actually had support from an AMD hardware software engineer for a while. One API was written on a support contract for Intel, and Metal is a pure reverse engineering of the Apple computing stack. But these are all open source and packages and driven by an open source community. So if you run into issues, if you have problems, there's an active community on Discord and on Slack, and we're happy to take your issues and hopefully make sure that you have a good time. But there is no SLA. You can't go to NVIDIA and say, hey, I have a bug in CUDA.gl. Can you fix it? You can try. I would love if NVIDIA were to get more involved, but these are all open source communities. So what I call magic of Julia comes from the fact that we have a strategy of abstraction, then specialization, and then using multiple dispatch. We use abstraction to encode behavior. So as an example, when you call transpose on a matrix, the array data type that is stored on the CPU, we do not outperform the transposition. We return you a transpose object that contains enough information that tells us, well, it is containing a matrix of float 64. Then we specialize on the type signatures of a function and use both a Julia-specific compiler that is performing abstract interpretation to remove type uncertainties from your program, and then perform some other language-specific optimization, and then goes to LLVM to produce optimal code for your hardware platform. And sometimes when you have very interesting and exotic hardware platform, as is often the case with HPC, it might need some work to make sure that we can produce the right SVE instructions on the new ARM chips. And then we use multiple dispatch to select optimized behavior. So as an example, when I take a matrix and a transpose of a matrix and I multiply them together, I end up by the dispatch rules in a low-level function in linear algebra.gl that is called mulbang, where I have one argument that is a transpose and the second argument that is a matrix. And it is calling into the gem wrapper, which is basically calling into OpenBlast by default, or you can also tell it to switch to any of the other BLAS libraries that you might want to use. And so this strategy of encoding behavior in the type domain, then specializing, and then using multiple dispatch to select allows us to write generic code that is highly efficient. The combination of Julia and GPU arrays.gl provides a high-level array-based programming environment. And essentially what we mean by that is that there is a vocabulary of operations that operate over arrays instead of over elements. Things like map, broadcast, scan, reduce, map, reduce. Think of those as your high-level operations and often operations that map naturally onto GPU parallels. But there are also library functions, like if I want to do a matrix multiply, as on the previous slide, I want to call into a library. But if I'm doing that operation with a CUDA array, I might want to use cuPLAS instead of my normal CPU plus, which I might not even be able to use. And so other libraries like FFT are also supported, sparse computations, and so forth. We use array types to store where memory resides and how code is executed, and use that information to determine how code is executed. And so what you might see in a parallel program is we have a matrix of float64, which is allocated on the CPU. We have a Q matrix, which is allocated on an NVIDIA GPU. And we have a ROC matrix, which is allocated on an AMD GPU. A key point is for us that data movement is explicit. I am not a fan of programming environments that make data movement implicit, where you do not know if a data buffer is being moved or not when you write your for loop. I should also add that this design came about before UVM was as prevalent as it is now, but I still believe there's a value in being very explicit about where memory resides and to move computation to the data instead of moving data to where you want to do your computation. And indeed, that is our guiding principle. For me, at least, compute follows data. We want to have the capability of minimizing data transfers and maximizing the amount of code we run on an accelerator. And sometimes that might be very silly, like some operations, you're like, why are you running this on a GPU? But you might avoid a very costly data transfer to do so. And so we work on supporting more and more of the language on GPUs. Some parts of the language cannot be supported on GPUs because of the programming environment being so limited, but many things can be. And so one of the very interesting things that we have decided to do is that array accesses in Julia are by default bounds checked. And this holds true for GPUs as well. So if you do an out of bounds operation, you get an error instead of maybe getting a data corruption later on. We have these different layers of abstractions. We start at the lowest level, where we have CUDA code. So this is a Julia function using CUDA is loading the CUDA.gl package. Then I write a sexpy kernel, and I use what you might see as normal as the primitives that CUDA provides us. So accessing the clock index, the clock dimension, the thread index. And then I can do my operation. And then I can use the add CUDA macro. Every time you see an add in Julia, that's a macro, to launch a kernel on the GPU with a specified number of threads and a specified number of clocks. Now I've mentioned there's a question in the chat if there is support for an OpenCL or SYCL backend. And yes, OpenCL.gl was for a long period of time asleep. But over the last year, Tim Bissard in particular spent a lot of work in making OpenCL.gl a very functional backend. And most recently has the fun thing of compiling SPIRV to OpenCLC so that we can run on platforms that don't support SPIRV. And then we have a layer of writing a generic GPU kernel using a package called kernel abstraction. And fundamentally, it is the same code, except that it allows you to be a little bit less verbose. So instead of asking for the index and calculating it manually, you can say, I want to have a global index. So it's much more closer to OpenCL in that way. And this bounce check also is implicitly happening, which has caused a little bit of grief. So there's a way of disabling this bounce check if you want to write code that doesn't need it. And you can annotate input arguments as an example as being const, as being not mutated within inside the kernel, which allows the use of LDG operations on directly. You also don't need to provide a return statement, so it's basically a little bit of a cleaned up version and a very shallow version that translates to this kernel above. And to launch this kernel, instead of using a macro, you instantiate it on a backend, here the CUDA backend, but I could also pick the AMD GPU backend, and in a future version of kernel abstractions, the POCL backend. Give it the arguments to launch on, and then give it this keyword argument called ND-range, which specifies the range of indices to visit. No, this is actually correct. It's fine. But you shouldn't write these simple kernels, but most of the time you don't need to. You can just simply use Julia's array abstraction. Here is the podcasting. So every time you see these funny dots in front of an operation, we're doing element-wise operations. And here, this becomes one fused GPU kernel that is essentially the same as these kernels above. Kernel abstractions is priced to be very minimal. It has a couple of utility functions like kernel abstraction.allocate to allocate memory, kernel abstraction.synchronize to synchronize a device, but mostly it differs to the vendor packages, and so they implement a very minimal API. It used to be much more complicated, but over the years we realized that we really don't need too many complications, and we want to just have a simple interface to writing a portable GPU code, but still in a GPU forward method. So what I mean by that is we want to write GPU kernels. We don't want to write parallel for loops, as an example. And so here is a translation guide. I have a CPU function. We have my index iteration. I replace that with add index global. I have the body of the for loop. And then I need to choose a backend. I need to allocate my memory. I might need to initialize it here to random numbers. And then I need to instantiate it and launch it. Note that in Julia, GPU execution is asynchronous, and I've seen it too often, so that I have to put it in my slides these days. When you do benchmarking, you need to synchronize the device. Otherwise, you're just measuring how long it takes to launch a kernel. And so there's a Julia package called benchmark tools, and you need to synchronize the backend after you are launching your kernel. While GPU operations are synchronous with respect to the host, they are, of course, ordered with respect to each other. So if you launch a bunch of GPU kernels, they're executed one after the other. We generally synchronize on access. So when you move data back to the host, we synchronize the device before that to make sure that you are getting the correct data and you're not copying data that is in the middle of being modified. This also lends itself together with Julia's task-based concurrent programming style, where each task in Julia gets its own independent stream of execution. And so I can parallelize my computations on one GPU without having to manually set streams and propagate streams through operations, which can be tricky because when I have an A times B operation, where does my stream go? And so the stream is associated with a task. And so I can use Julia's task parallelism to run code in parallel on one GPU, but also on multiple GPUs if I switch the device within my task. I've been talking about some sense of portability. I want to clarify that a little bit. For me, an application is portable if I can run it at least. That's a bare minimum. I want to run it on different compute architectures. Those should be either different CPU architectures, but we also live in a multi-GPU vendor world. So I'm really uninterested in programs that only run on one GPU vendor these days. But also they should be able to compute the same thing, because that influences whether or not I can develop on one platform and move to another later. And this is a topic that is very underexplored. Like, if I use special functions, how precise are different vendor libraries? And can I validate a programming on NVIDIA's architecture and then move it to AMD and expect the same behavior? Atomics are a big open issue of semantic woes and confusion. Float 16 has been one of those topics that is tricky, where sometimes people go to performance over correctness and portability. Then one aspect of portability that we shouldn't undervalue, of course, it's performance portability. And here it is tough, right? Kernel abstractions makes portable programs. It does not necessarily make performance portable programs. This difference is less severe than it used to be with OpenCL, but those of you who've been in this game for long enough might remember talks from NVIDIA why they have to have CUDA, because OpenCL does not give enough performance on NVIDIA GPUs. I don't think that was true back then. It isn't true nowadays, but it is true that for different microarchitectures of different GPUs, you might want to write different programs. And we see that often. And kernel abstraction doesn't really say anything about that. It just allows you to write GPU programs that can be executed on multiple backends. There's a question by Jonas. Why is a backend not tied to a device? A backend is not tied to a device mostly due to unified virtual memory. So I can allocate an array on one device and use it on a different device without problems. And so you might have you might have the virtual memory subsystem then migrating your buffers, but this is where we're living nowadays. It's really hard to say, well, this array was allocated on this device because it might actually have been bounced to the other GPU. So the backend just says which compute vendor is responsible, not which actual compute device it's being executed on. But one other aspect for me, at least, for portability is, can I use platform-specific capabilities? So I might develop a float16 program on an x86, and I expect it to give me the correct answer. It might not be fast, but then if I go to A64FX and I run my float16 program there, I want it to be able to take advantage of the fact that that is a native floating point capability of that CPU. But this also means, in some sense, in Julia, we can specialize. And so we could specialize on the GPU vendor or the GPU hardware and make sure that we have a very fast kernel, depending on if we're executing on an AMD or an NVIDIA. They might both be written in kernel abstractions. They might both be written differently, but we can switch and take advantage of the code patterns that provide the best performance. As I mentioned before, adapt.gl is a very small package. It has this nice property that I can give it an array type, and I can give it a complicated structure that I want to translate to the GPU. And so after the call, I will get an object that is the adjoint of a q-array. If I want to do it myself, as an example, I might have this model struct that contains some data. I have to define this adapt structure call with a free to and then a specialization on my model. And then internally, I just reconstruct that object with my data. This is important so that object can pass from the CPU to the GPU, but also from the GPU host side to the GPU device side. So as an example, a q-array will be turned into a q-device array when it is being passed to the kernel. So putting it out together, giving you a concrete example. This is from an old question on discourse, on the Julia discourse, where somebody was like, well, I've written this program. How do I port this to the GPU? How do I execute this on the GPU? And I will leave these two calls as a question because there are things that have changed over the years. But generally speaking, the only thing you need to do is you need to say, well, my X, which is an array, my Y, which is an array, and my W, which is also an array, those now should be q-arrays, or in the kernel abstraction parlance, I adapt them to a specific backend. And then the entire code should follow where the data is and will execute on the GPU. And I didn't include this plot yet, but here's an example from back then where we measured the performance, and the blue line is the array execution and the red line is the q-array execution. And we see what we often see with GPU codes. If the input side is too small, it doesn't make sense to run on the GPU just yet, but then later on, the GPU is a much faster execution environment up until the point where we run out of memory. Loss W and loss B, those can be implemented with a host of different automatic differentiation libraries provided in Julia. And we treat automatic differentiation and GPU acceleration as orthogonal problems. So it is not like in Python, where the choice of GPU acceleration library also binds you to a choice of GPU acceleration. So essentially, PyTorch, JAX, and TensorFlow are all ecosystems that are very closed off. They try to provide the same APIs with NumPy, but In Julia, we try to be less opinionated and give you the freedom to experiment with different AD frameworks. And some support GPU computing better than others. And I have to touch my own nose there because Enzyme, which is a AD framework I work on, probably supports GPU computing the worst, but we're also working on it. Okay, so there's a question in the chat about SYCL. Right, so SYCL in itself is very C++ oriented, if I remember correctly. I have not looked that much at SYCL. But under the hood, it is very much OpenCL. So for Intel, which is a big component of SYCL, they use one API underneath the SYCL implementation, and we use OpenCL plus one API, or like, yeah, to directly target Intel GPUs. So that is less, because SYCL is such a C++ thing, we don't directly support SYCL. One of the party tricks of Julia is that you can write your own custom array types. And here in this notebook, I can switch my different GPU computational backends. I can either use a CPU execution or I can use a CUDA backend. And I have my matrix type, which basically contains an array, a vector, and I can define when I index any element of my matrix, I can define it based on this vector. And this is an example that comes from Alan Edelman, my professor at MIT, who basically says, well, we have a vector that gives us a diagonal and then also the off elements. And I want to now implement a custom eigensolver that uses the fact that I have this custom matrix type to accelerate the calculation. So first of all, I define, as I said, my adapt structure function so I can move the data type to the GPU. And if I want to, I can I grab some random data. And essentially, this is the matrix that we want to calculate the eigenvalues of, or the maximum eigenvalue of. And we can also construct our matrix M from X, and then visit all of the points, and we can double check that indeed all of the values here are the same as through this construction. So now we have a matrix type. It's basically using much less storage to represent this operation. And I can use linear algebras, Eigmax, to calculate the maximum eigenvalue. But I can also use a series of high-level array operations, MapReduce and maximum here, to write my own Eigmax solver, particular for this matrix type. And this is, for me, the crucial point. This is something we can expect domain scientists very much to write. We might not want them to write low-level kernels, but certainly writing functions based on high-level array operators is something we should encourage everybody to do, because they are often much more clear in what they are, in their meaning. And so here we just have an iterative algorithm. And one thing we should emphasize is that every time we call f here, we are going to the GPU and we are waiting for the GPU. So this is one of the downsides of the high-level array style. When we go to the GPU and we want a scalar back, we have to wait for the result to be computed. So iterative algorithms like that are, of course, always a problem for this. You might see this as well in bigger simulation codes, where you have at the end a norm to decide whether or not you're done yet. And calculating that norm would cause a pipeline bubble. And so I can now call Eigmax of my matrix X, And we remember the highest eigenvalue is 993, and here it is again 993. Very nice. And as if by magic, I move the data to the GPU. And to just show you that I'm not cheating, now my matrix type consists of a Q array. And I can run this code again, now executing on the GPU directly, and I get the same answer. CUDA.gl in particular has a very nice integrated profiler, which does not exist yet for AMD GPU or for one API. If anybody wants that, open an issue. It should be possible, but it's also, these are all very vendor-specific things. How do I get performance information out of my GPU? And we can look at the host side activity here, and we can look at the device side activity of the code. And so on the host side, we mostly have things like launch kernel, memcopy device to host, a memory allocation, and a synchronization operation. And then on the device, we have a couple of MapReduce calls, one of them being maximum, and these ones being, I think, yes, these are the calls to F here. Now, one idea as an example to show composability, if I wanted to optimize this, I might have the idea that it's quite inefficient to first do a MapReduce and then to do another MapReduce. Wouldn't it be nice if I can just use these two MapReduces together? And so here I've written a function that I call delta, which uses static arrays. Static arrays are basically stack allocated small arrays in Julia. And one of the elements is, one of the calculations is F, and the other one is F prime. And the compiler will actually make sure that, common sub-expression elimination happens between those operations. And then I do a map reduce operation with G, which is my anomalous function here, and the plus as a reduce operation, and I can calculate F over F prime, which is essentially this line, F over F prime. And now I can write my argmax2 function that now uses my delta function here to do this calculation. And again, I can make sure that the answers are the same. Well, actually, the answers are now slightly different. That is due to the different accumulation that is happening. And now if I run this code, I see in my profile that I think the number of this is profile of argmax again. So I have 28 copy device, and this has now shrunk to 15. And these are the pipeline bubbles caused by calling MapReduce and copying a scalar value back to the host. And I can also use benchmarking to confirm that this code is actually now slightly faster. It's not much faster. So 1.5 milliseconds versus about 1 millisecond, but it is faster a little bit for this entire code. If you want to know more about writing custom kernels, today in my class on research software engineering here at the University of Mainz, I had this notebook where I basically walk through a couple of examples from like a very simple copy kernel to then a transpose kernel, and using shared memory, local memory, to do operations, using the profilers, how to deal with data races, how to write a matrix multiply with kernel abstractions, and so forth. So that is linked here, and you can execute it in Colab, which recently added support for Julia. Okay. I think I have a little bit more time, but now would be a good moment to pause and ask questions if there are anything.
Yeah, I think if anyone has any questions for Valentin, oh, I see there's a hand up from Charles. I was about to say raise your hand. Charles said exactly the right thing. Go ahead.
Yeah, thanks. This has been a very, very interesting talk. I've got a couple of questions for you. First of all, does Julia support fat binaries so I can build a binary with multiple GPU backends and then run it wherever, without having to recompile on an AMD or NVIDIA GPU?
No, but kind of. Um, so the problem here is that this is all just-in-time compiled currently, and so you can cache compilation. So the GPU compiler GL has the disk cache that is available for about now half a year. So you can cache the compilation if that is a concern and if it is taking too much of your time. But generally speaking, we are not yet at a point where we do anything with fat binaries, mostly um, because Julia itself is does not yet have a very robust like compiled to one's own single binary story. There has been a lot of movement in that regard. So Julia C is being an experimental feature for Julia 1.12, but the GPU integration for that is yet to be determined.
All right. The other question that I have is, what happens if you have a data type which is, say, double precision, and you offload it to a GPU which does not have double precision support in hardware? Is it going to be able to do an emulation of that?
No, but I want to. Well, actually, so there is a package called double floats, floats.go. Um, and I think you can, um, you could in theory create a double float of float 32, which is a very weird, notion, right? Basically, we are using double floating point arithmetic and then use two float 32s for that and to get more precision. So that's possible. That should work on the GPU, but currently we are not emulating float 64 arithmetic on, I say, Intel GPUs, which currently which some don't support float 64 yet. But I want to do that. I just haven't found the
So
time to
you
implement
basically
it.
have to know ahead of time what your hardware supports to use that package. It's not going to switch it in automatically.
Right. Right now, there is an option. You have to know I'm going to be executing on Intel. I'm going to use a double float package to make it work. But yeah, I would want to do that automatically, and we do that as an example for float 16 or B float 16. We do this software legalization.
All right. Thank you very much.
Okay, thanks for the question, Charles. There's a comment from George about the fat binaries. Are there any other questions people would like to ask now before we let Valentin wrap up the presentation?
So towards the fat binaries, yes, I mean, there are many different versions of GPUs, and I am a proponent of giving my users choice, as particularly because maybe depending on where you deploy, but getting a working and functional CUDA installation and an Intel installation and an AMD installation will take a lot of storage. And so in Julia, we try to make things work by default. And so we have a system called binary builder GL combined with Yggdrasil that will deliver binaries to the user from external dependencies. And so we try to avoid adding the GPU render packages as direct dependencies because they come with a bit of baggage. And so recently we've seen more of a trend of people writing generic simulation libraries like Oceananigans and a CFD simulator developed at MIT. It's basically the successor to MIT GCM. And you can load the AMD GPU package and Oceananigans, and now Oceananigans can do calculations on AMD GPUs. That's at least the dream, that's the goal, that's where we want to be. Okay, just briefly, because I promised in the abstract to talk a little bit more about the compiler. One thing I want to emphasize is that while I call Julia a dynamic programming language, a language being dynamic is a spectrum. Most often we talk about this in terms of the type system. So we can have types that are checked before runtime or types that are being checked during runtime. We can think about this in terms of variables. Do these variables have a fixed type, or does this variable can change types? But for me, more interestingly, is the amount of code that I can look at closed, or can the user add more code during runtime? And so a lot of dynamic programming languages have this feature called eval, where they add code at runtime. And then a weird one that people don't tend to think about as much is, can the struct layer change? So can I change the fields of an object class struct at runtime? In Python, it is scarily, the answer is yes. I can take a single instance of a type and I can add a new field to it, and nobody's going to yell at me. So Julia has a dynamic type system. We have open world semantics, but as an example, our struct layout is static. Once you define a struct, you cannot change it. We are playing with that a little bit. In 1.12, you can redefine a struct, but it doesn't change the notion of, in one view of the world, the struct layout is defined, well defined. So we can use that information to optimize allocations. We can use that information to optimize your code. So when we look at compilation, Julia uses LLVM. And so you have the traditional compiler stages. So you have some parsing, you have some lowering. Then we perform abstract interpretation, base type inference. So this is a process that can return any, so uncertainty. It is okay for Julia to figure out that it can't figure out what your code is doing, which will give you slightly worse performance, but your code will run. And so we have tools that will tell you about when type instabilities occur in your program. And the GPU compiler will yell at you very loudly when you feed it a program that has a type instability. Then we have a series of high-level optimizations. Then we perform code generations to LLVM IR. Then we have lots and lots of optimization in LLVM itself. And this is, of course, one of the great benefits of using LLVM. The C++ folks also work on LLVM. And so when LLVM gets better, Julia also gets better. And then we go to the LLVM backend. And some backends are great, and other ones are not so great. And we have to turn off the recording for me to tell about my least favorite backends. And then we can look at the native code. As an example, in CUDA, we have a couple of macros that allow me to introspect what my code is doing. And so I can use this macro called add_device_code_LLVM, which will allow me to basically snoop on my compilation and look at the LLVM IR that Julia is generating for this podcast kernel that I care about. And this can be very useful. Of course, this can also be too much information. So this is something where I would say knowledge of what the underlying platform is going to do is really important. But you can take this one step further and you can ask for the NDPTX of this code. And now we have to rely on NVIDIA and NVIDIA's documentation of NDPTX, but we can try and understand if there are inefficiencies. One example is maybe we are using too many in 64 operations. And then I can, of course, go to the output of this step. So SAS is the now device-specific NVIDIA assembly, and this is often better to read when you are actually doing some profiling and you're using Nsight. But the ability is there to understand very much in detail what my code is doing. This might remind you of a website called Compiler Explorer /Godbolt. And this is very much right. I just do it in my REPL or in my Pluto notebook. I can introspect what my code is doing. But Compiler Explorer also has Julia support these days. And so I can also just do it there and share the results. I think the GPU stuff does not work there yet. Because we didn't want to make Matt sad by adding all our compute stacks to his Docker containers. And with that, I've done everything I promised in the abstract, and happy to take more questions.
Yeah, thank you so much, Valentin. You did indeed cover a lot, so we're very happy to open the floor to further questions.
One thing I would want to do is the Julia Lang community calendar is a very useful thing. And as an example, tomorrow, Jose Girano and I will host the HPC monthly call, a monthly meeting at a convenient time for people in Europe, where we talk about using Julia in HPC. And then next Monday, as an example, Tim Bissard and I are hosting the Julia GPU office hours.
Yeah, thanks for pointing that out, Valentin. There's a question from Guillaume. I don't know if you just want to ask it, Guillaume, or should I read it out for you?
Yeah, I can. Thanks, Valentin, for the talk. I was just wondering, there's a lot of very active development on a package called Reactant, which, for those who don't know it, is a kind of Julia equivalent to Jack's compilation. This is with very, very heavy air quotes. And so I'm wondering, how does it replace or complement or compare to kernel abstractions in terms of facilitating GPU and TPU programming?
So Reactant is a very fascinating project. It, interestingly enough, reuses the GPU kernels. So it takes CUDA or kernel abstraction GPU kernels and then uplifts them into MLIR and uses that representation to perform additional optimizations, and then retargets your GPU kernel to TPUs or retargets it back to another GPU. So it is definitely, I feel it is still at a research stage, but it is also an answer to the question of, well, how do we perform complicated optimizations that the Julia compiler currently is unable to perform, like loop fusion or GPU-aware loop fusion, even worse, today, or maybe also in 2 years. But my hope is also that maybe the Julia compiler learns a little bit more of these capabilities, and that over time we take the best ideas from Reactant or from other compilation strategies, and we add them to the Julia compiler where it is reasonable to do so.
Thanks.
Thanks. Any more questions? Uwe, you go ahead.
Yeah, hi. Thank you very much for the very nice talk. I have actually a question about the support of NVIDIA or any vendors for the now open source projects. Is there anything, when you look in the glass ball or something like that, is there anything in the future that the Julia libraries for the vendor specific stuff are supported by the vendors itself? Is there anything planned or anything in the backyard which we don't know?
This is an unknown unknowable. In some sense, We have had positive vendor engagements sometimes. It often depends on very specific engineers being passionate and interested, and I had very good experiences with AMD in that regard. But there has not yet been somebody on a C-level strategic investment call, right? And this is often some vendors can be very frustrating to work with because you ask them and you have a bug and they ask them to fill that in their internal bug tracking software, and you don't see anything until 6 months later they tell you, we fixed it, please update. And
Okay.
that is not how or why. I like AMD's compute stack a lot because it is open source and because I can debug it myself. I'm also frustrated by it, how fragile it can be, and how sometimes it's hard to get changes in, but that's a different debate. But at least I can debug it. Whereas with NVIDIA, as soon as I give it to one of the NVIDIA tools, something's happening. I mean, Intel should also be praised, but I've personally worked a lot less with Intel, mostly because it's so damn hard to get any GPUs of theirs.
Okay, understood.
But
Thanks.
there hasn't been any like vendor who's like jumped out and does it's like, well, all our customers are asking for Julia support. How can we help you? It's mostly, oh great, you're adding support for us. Here's a GPU so that you can run CI. And I'm like, that's great. Thank you.
Yeah, better than nothing. Yeah, it is.
Yes. I think it is a testament to Julia's flexibility, how good our GPU support is with how few people are actually working on it.
Okay, thanks for your answer. And thanks for the talk.
Yeah, thanks for the question, Uwe. So time gets on, but we could take probably one more question if there is something burning. Last chance. Okay, I will, yeah, I don't see anything else. So in that case, thank you very much to Valentine. And just before we close, Sanya's just wanted to give us a few words of closing and reminding about a few things.
Yeah, thank you also from my side. I just wanted to mention, especially for people who are already in the EVAS network or who would like to become the EVAS network, we also have a Mattermost team. I'm sending the invite link in the chat right now, which you can access. And the Mattermost team, the idea there is that you can just directly talk with other people interested in research software quality or research software engineering. It doesn't matter if you are from a specific field, we are open to all sciences. It can be on direct outputs, especially for the RSQ kit. And also many of us EVAS project members are there. So if you have any direct questions for us as the project, you can also send them there. As mentioned at the beginning, the webinar series will be continuing after the summer break, so in September. And we will be inviting members from African RSC communities, and we will go on with further training sessions. We've seen that the interest with collaborating with the science clusters work quite well, so we would try to get them on board too. So the other science clusters, so far we had the environmental science cluster with us, and we'll also be focusing on the outputs from EVAS directly. So this is it. If you have questions for the EVAS network, you can find all our contact information on the webpage. If you want to join the network or for the newsletter, all the information is there. I say thank you at this point to Valentine for the talk and to everyone who joined and listened during this time. And great that we had the opportunity to co-organize it with the CAF. And I wish everyone a lovely Wednesday evening or rest of the day, depending on